Welcome to the presentation, Onset of Creasing in Polymer Membranes. My name is Kawai Kwok. I'm an assistant professor at the Mechanical and Aerospace Engineering at University of Central Florida. So this work has been mostly done by my students, Annan and Annan Mashin. So just to give a little bit more information on this study, so the motivation is on deployable film membrane structures. As we all know that film membranes can be stored and packaged very compactly, and they deployed in space as very large area structures, and you can use them for many applications. For space, one of the most remarkable applications is the solar sail. For example, the JAXA Icarus is a very successful solar sail mission making use of film membrane structures. And there are many other membrane structures or spacecraft structures concepts that are based on film membrane structures. Some of the examples are shown here. So the one of the most important part of designing a film membrane structures is the creasing of that membrane, because for the membrane structures to be able to fold and deploy in a systematic manner, they have to fold according to some pretty fine crease patterns. And for polymer membrane structures, the creasing is typically done by inducing permanent deformation, and that is, for example, by compressing it to form a crease. That process has been investigated in many different ways in the literature. So some of the related studies are quoted here. Basically, the process goes like this, right? You have a flat membrane in which you apply a compression, and to an extent that you leave behind a permanent region of crease with a finite rest angle or equilibrium fold angle, and there is at that crease is a permanently deformed region. It has different mechanical characteristics than the rest of the membrane, and to put it flat, you do need to apply a tension. It would not actually go completely flat because the crease region has been permanently deformed. And the previous studies have investigated the folding force, the rest angle, the unfolding mechanics, and the stiffness of the crease sheet very thoroughly. But there are two questions that are still open. One of them is the time dependence of the creasing process. There are experimental evidence to show that the crease angle and the unfolding mechanics actually depend on time. So they're not purely an elastic plastic process. And also that the load histories is actually important when you crease it, because different loading histories actually can give you a different resting crease angle. So the mechanical characteristics are going to change depending on the load histories and time. The other question is regarding the material origin of creasing. Right? It has always been assumed in the literature that plasticity is the origin for creasing. However, there is also experimental observations that there is fracture happening at the crease on polyimide film. So the objectives of the current study are trying to address these questions experimentally and eventually through analysis. So we like to investigate the time-dependent behavior in creasing for polymer membranes, and we also like to try to correlate whether the onset of creasing is related to polymer yielding. We started off with a study on the U strain on Kapton. So we used thin 25 micron Kapton as the material for study. We first performed a uniaxial tension test at constant strain rate to just to understand how the U strain and U behavior for that material is. You see here, this is a stress strain diagram for Kapton. 6 different tests. They all stretch to different strain levels from 1% to 6%. Because this is a viscoelastic material, we do leave behind 96 hours of free recovery time before we do any permanent strain measurements. And in this case, we found that the U strain is around between 3 to 4%. You can see on the right hand side there is the evolution of the residual strain we measure throughout that 96 hours. So for a sample set stretched to 4% or above, we do see a U strain. So the U point is between 3 and 4, and as we go higher maximum strain, we do accumulate more plastic strain in the Kapton. So next, we started to look at the creasing of the membrane. So the experimental procedure, we followed the procedure that has been established in the literature, and that's by a compression test on a membrane. So we take this Kapton film, tape it at the end, make a loop, and apply compression. So what we have done differently than the literature is that we do take into account the time dependence a little bit more carefully. We allow the membrane to recover after creasing for 96 hours without any load before we do any sort of measurements on the crease. And the second aspect that is different is the compression force range that we apply. We apply a small compression force range, and that is because we like to understand and to characterize the onset of creasing, not a heavily creased, fully creased membrane. So on the right hand side, you see this is an example of the experimental result. We have a membrane that is has been creased. On the bottom, you see there's a low zoom picture. You can see there's the permanent rest angle. We zoom in the crease region, we do see a curvature, which we characterize by microscopic image analysis. So the result is shown here on the crease curvature. So we look at the permanent curvature that is at the crease, and we have actually done this creasing test two different ways at the same force levels. So the first type of loading is we call it no constant load. Basically, we apply the compression force to the specified load, and then we immediately unload it, right? And the second type of load profile is constant loading profile, in which we go apply the same load compression force to that specified level, and we leave that there for another 300 seconds before we unloading. So that is represented by the orange line here, which says 300 seconds of constant load. So that's quite a big difference in the permanent curvature that is resulted from these two different load profiles. Right? Even though 300 seconds is not a lot of time, it's only 5 minutes, we do see that we accumulate quite a bit more permanent curvature by doing that, at the same force levels that we reach. Right? So another interesting point to point out is that there is a point where there is no crease created, and that is the point where we have applied a force of 0.05 Newton per millimeter, and we immediately unload, so there's no constant loading segment in the test, and this is where we see that there's no permanent curvature that can be measured. Once we go beyond that, we do see the next test that we go to, which is 0.1, that does have a residual curvature, and so the onset is somewhere between 0.05 and 0.1 if we look at the no constant load case. Let's take a look a little bit more closely at this particular 3 data points. So again, this is the point where we have no creasing. This is concurred by the just visual observation. There's a flat membrane after creasing. After the creasing test, it still maintains its flat configuration. However, if we go look at the same force level, but there's an additional 300 seconds of that loading, the behavior has changed. We have a membrane that has maintained a permanent curvature, so there's a crease and there's a permanent rest angle, and so that the time dependence of the material really plays quite a bit of a role in how you obtain the crease angle, and it's actually quite a strong dependence because 5 minutes is not a lot of time. Another observation we make on this case where we have no crease, we flip the membrane around, we found that actually there's a small crease line on the compression side, so it really tells us that the creasing actually begins on the compression side. So we did a quick finite element simulation of the whole process, making use of linear viscoelastic model based on Crony series. We also have just a 2-dimensional plane strain finite element model to try to correlate the strain and the creasing. So we do find that actually the tensile strain actually happens before creasing. So to to be able to accumulate some measurable permanent curvature, we do have to go beyond the plasticity, beyond the. So to conclude, there are two findings that we have find in this study. The first one is that the creasing of polymer is highly time dependent. So if we want to create any creasing criterion, it must be based on the load histories and not just the critical load alone. And the other observation is that creasing actually begins on the compression side, and so there is likely some brittle fracture happening before plasticity. That's all my presentation. Thank you for listening.